All right. Good afternoon. Today we're going to be looking into some new material, and then I'll just give you some details regarding test one details and the deadlines and all that, and just for kind of the new material. Okay, so in chapter one, okay, we'll be looking into what are regarded as functions. Okay, and we've been looking at those in a sense whenever we have been working with algebraic expressions, like in terms of combining and also looking into equations. And now, for what we have in terms of like what makes a function a function. Okay, well, in the case of a function, okay, there are some features that will separate some of the algebraic terms that are functions apart from those that are not. And for what we have in the case of a function, okay, so if you think of like the xy coordinate system, we have for a function, okay, we're going to have a mathematical relation. And let's say that for what we have where in the xy coordinate system, we're going to have for each x value, okay, there's going to be one and only one corresponding y value. Okay, now just place emphasis on this case. You have one and only one. Okay, and now just keep in mind, okay, for ordered pairs or points in the xy coordinate system, okay, so we have all ordered pairs. Are of the form xy. Okay, so you have x coming before y. And just for, in the case of what is regarded as x, okay, in terms of functions, okay, now x is regarded as the independent or input variable. And for y, okay, y is going to be the dependent or output variable. So the output is going to be dependent upon what goes on with the input. Okay. Now, in terms of what we have regarding functions, okay, like in terms of there are various ways that functions can be presented, and a common introductory approach will be with sets of points or ordered pairs. And let's say we have determining whether the set of ordered pairs will be a function or not. And we'll say, for instance, okay, we'll say we have a set of ordered pairs. Remember, okay, so you have ordered pairs to be the form x, y. Okay, so we'll say that we have negative 1, 1. As well as 3, 4. And also 5, 7. Okay, and if you notice, okay, we have to be a function, okay, for each x value, there is one and only one corresponding y value, okay. So if you notice, you have with the x values, okay, we've got negative 1, 3, as well as 5, okay, and negative 1 is paired up only with 1, 3 is uniquely paired up with 4, and 5 we have uniquely paired up with 7. Okay, and so in this case, you're going to have this to be a function. All right, now for what we have in the case of next set of values or ordered pairs, and we'll say we have say you have 3, negative 4, and say we have 6, 7, and 9, 10. Okay, and if you notice, okay, so you have, again, to be a function, each x value must be paired up with only one corresponding y value. Okay, so you got your x value at 3, and that is paired up only with negative 4. And 6 is uniquely paired up with 7. And 9, our remaining x value, is uniquely paired up with 10. Okay, so that is also going to constitute a function. Now let's say we have like negative 1, 2. Four, 5. 3, 7. 4, 9. And 10, 3. Okay. All right. And if you notice, okay, so if you notice with the x values, we have negative 1 followed by 4, then we have 3. Notice we have 4 to appear once again, and finally we have the number 10. And in the case of whether we have to be a function or not, again, for each x value, okay, there must be one and only one corresponding y value. Okay, so you got negative 1 is paired up only with 2, and like 3 is paired up only with 7, 10 paired up only with 3. But guess what we have with the number 4 as the x value? Okay, it's paired up with 5, and it is also paired up with 9. So here, for what we have in this case, all right, so this is a set of points where you had the same x and different y values. You got the same x and different y values, and for what we have in consequence, okay, is that for this set of ordered pairs, okay, the answer to this question is no. Okay, now let's say if we have for sets of order pairs. Okay, so if I have 0, 1, 1, 1, 2, 1, and 3, 1. Okay, and if you notice, okay, again, to be a function, okay, each x value must be paired up with only one corresponding y value. If you notice, we have 0, 1, 1, 1, 2, 1, and 3, 1. So that y value of 1 repeats, okay. But looking at it, okay, so we have your x value of 0, and guess what? It's not paired up with any value but 1. Likewise, for the x value of 1, that is uniquely paired up with 1. Same thing for x equal to 2. Okay, that is paired up only with 1. And we have for x equal to 3, have that also paired up with 1. So it turns out that this is going to be a function. Okay. Now, one might wonder, okay, so but you got the repetition, okay, with the y value. And you can have a repeating y value, but if each x value is paired up only with one y value, it is still going to be a function. But now let's say that if I switch the order of the coordinates, okay, so transitioning to 1, 0, 1, 1, 1, 2, and 1, 3. Okay. And if you notice, okay, we're going to have, so you have your x values to repeat with 1 throughout, and guess what? You have it paired up with 0, with 1, with 2, and with 3. And like for what we have in case 3, and perhaps with a bit more dramatic flair. Okay, so you have same x, different y values. And so for what we're going to have in this fifth relation, okay, that is not going to be a function. Okay, and let me mention some things here. In a function, the x values make up what is referred to as the domain. And also in a function, okay, now the y values will make up what is referred to as the range. And just a couple of quick cases here. If I were to determine the domain and the range of each function, we have, like in the first case, right? So we'll say we have let's say we have 10, 7, negative 1, 5, 4, 7, and 3, 9. Okay, so for looking at what's going to make up the domain, okay, again, so 10 is only paired up with 7, negative 1 is paired up only with 5, 4 paired up only with 7, and 3 is paired up only with 9. Okay, so in looking at what we have in terms of identifying, okay, the domain and the range, there's still a little bit of color coding. Okay, so for your x values, okay, so you got 10, negative 1, 4, and 3. So if I write this as a set of elements, okay, so you got 10, negative 1, 4, and 3. And the order does not really matter, but you might typically see it with the values in increasing order. So we have, like, out of the set, you can write this in increasing order, like negative 1, 3, 4, and 10. Or you just have a different order. It could be jumble, like 3, 10, 4, negative 1. But as long as you had those 4 elements, you have the domain. Now for the range, okay, so you're looking at the set of y values. Okay, so we got 7, then we have 5. Notice that 7 reappears, but I already have 7 down. So if you have a repeating element, okay, you don't have to put it down twice, like in the case of identifying the domain and the range elements. Okay, we do have 9, which has not already been mentioned. Again, if I were to express an increasing order, okay, so I have 5, 7, and 9. Okay, now let's say if I just have it as 1, 4, 5, 4, and 11, 4. Okay, so looking at what we have for the domain, again, we're looking at the set of x values. Okay, so we have, out of this case, they have 1, 5, and 11. Again, for the range, you have only one value. Okay, so you have 4, 4 again, 4 again. And again, you just need to put that element down only one time. Okay, so for many functions, okay, you can have repeating x or y values, okay, and so the number of distinct elements from the domain does not have to be equal to the number of elements in the range, and vice versa. Okay, so and this is a case of where you have different numbers of distinct elements in the domain and the range. Same thing here from the earlier case. All right, now again, so for functions, for each x value, okay, there has to be one and only one, or at most one and only one corresponding y value. And let's say that for in the case of graphing, And so I just kind of refine the definition. See, there is a technicality, but I'll save that for the graphing part. Okay, now in graphing, a function will satisfy, okay, what is referred to as the vertical line test. And what we mean by the vertical line test, okay, is that a vertical line will intersect, or I should say will meet or intersect the graph of a function and we'll say we have at most 1 point. For all x values. Okay, so this is just sort of taking a visual display, and let's say that sort of symbolizing that for each x value there will be at most one corresponding y value. Okay, so in terms of whether we had the graph to refer to a function or not, and we'll say that we have, for starters, okay, and we'll say that we have let's say you have a straight line, and we have with the x and y coordinate system, so you have the y-axis, okay, runs vertically, the x-axis runs horizontally. Okay, and we'll say that we have and just doing a bit of a quick sketch. And we'll say that for this particular function, okay, we'll say that we have that y is equal to f of x. And f of x is a functional notation which we will use, okay, for the letter y. And I'll get into those details in a moment. Okay, but you have that y is equal to f of x is equal to 3x plus 4. And for what we have in the case of the vertical line test, okay, so if I take a vertical line and say if I run it through the graph, okay, and if you notice you have for each x value you have intersection at most 1 point. So in this case, y is equal to 3x plus 4. Okay, that is going to be a case of a function. Okay, now let's say if we have situation, okay, and we'll say that we have we'll say we have some segments that are disjointed from one another. And in terms of whether we have a function or not. And again, just applying the vertical line test. Okay, so if I run from left to right, okay, so you have running exclusively through the first line segment. Okay, so you have intersection at most 1 point. Same thing for the second line segment. And you have for the third, okay, so you have intersection by at most 1 point, and for the gaps, no point of intersection, so there's really nothing that we have in y, but where you do have intersection to occur, you have by at most 1 point. Okay, so for these three line segments, okay, so that is going to be a case of what we have with a function. Okay. Now let's say that if we have a setup of line segments. Okay. And if I look at seeing whether this arrangement is going to be a function or not, and looking at applying the vertical line test. Okay, so as I start out, let's say from the extreme left, I have intersection at most 1 point. But once I start getting closer to the second line segment, guess what? So you have for the same exit value, you have 2 points of intersection. And for this particular arrangement, okay, where we had a function before, because you had for any x value, you had the intersection by at most 1 point. But let's say that for this x value, which is located to the left of the y-axis, okay, you had 2 points of intersection. Okay, and so we have so you have 2 points of intersection at the same x value. And for what we have in consequence, okay, is that this is not a function. Okay. All right. Now, for what we have now, for something that one might be inclined to think of as being a function, and say have like in geometry, and we'll say that we have a common graph let's say we have, in the case of a circle, and for what we have here, okay, we'll have centered, we'll say at the origin. And we'll just let this circle be defined by the equation. Okay, so you have x squared plus y squared is equal to 4. Okay, and we'll say that we have, again, for the ordered pairs, so you have 0, 2. 2, 0. 0, negative 2. And also negative 2, 0. Okay. And if I apply the vertical line test, okay, so just if you notice, okay, once I get, say if I start from the left, okay, once I get to the right of the edge point, negative 2, 0, I already have for the same x value. Once I start to enter the circle, again, I have 2 points of intersection. And for a full circle, in this case, full circle, that is not a function. Okay. Now let's say that is there any portion of a circle and let's see. Okay, and now if I have something like the upper half of a circle, okay, and say if I have a semicircle, and I'll have that like for this particular case, and we'll have like for the variation on this one, okay, so you have like y is equal to the square root of 4 minus x squared. So this is going to represent the upper half of the circle. And if I have this particular half laid out like upper half, lower half, again, if I run through okay, so if I go from left to right, okay, it is there, okay, that you have the vertical line to run through, okay, the semicircle, and the activity is now above the x-axis, whereas before with the full circle, I have the vertical line to run through both halves, but just cutting out a half, like an upper half or lower half, it turns out that an upper or lower half of a semicircle, okay, that is going to be a function. And again, you have the intersection between the graph of a function and a vertical line, where the intersection will occur by at most 1 point. Okay, so a semicircle can be a function, but a full circle cannot be. All right, and for what we have, again, so for functions, for each x value, there will be at most, okay, one corresponding y value. Okay, and again, to be a function, it must satisfy the criteria for passing, okay, the vertical line test. Okay, where you have the vertical line will run through the graph by at most 1 point for each corresponding x value. And now, in the case of what I had mentioned for the first function that I had brought up, and this is where we had y is equal to f of x is equal to 3x plus 4. Okay, now again, the f of x is what is referred to as functional notation. And just the layout again, so you have it could be other letters too, like G or H or B, let's say. But the most common notation, okay, that you'll likely see is going to be f of x. Okay, it could be y is g of x, h of x, z of x. And again, just for a given function, y is equal to f of x, and f of x is going to be the functional notation counterpart for what we otherwise say is going to be y. Okay, and again, just to restate for a function, x is the input or that which is independent, whereas in the case of what we have for y, y is going to be the output which is dependent. And for what we have in the case of functional notations, okay, common introduction with functional notation is going to be along the lines of determining functional values and expressions. Okay, so for what we have in the case of determining functional values and expressions, let's say we have as a case, right? Say if I have given y is equal to f of x, and say we have is equal to x squared minus 3x. And say if I were to determine let's say we have f of negative 3, f of 1, as well as f of x plus 2. Okay, so again, you have f of x, functional counterpart to what we otherwise say is going to be y. Okay, so we got for looking at the inputs at negative 3 and 1, and if you change the input x, okay, to x plus 2, you want to find out how this is going to affect the output, which we have represented by f of x is equal to x squared minus 3x. Okay, So first of all, okay, so if I'm looking at f of negative 3, okay, so the x value we have at negative 3, and then for the output, okay, running in line with x squared minus 3x, where x is at negative 3. So you're going to have in the follow through, we're going to have the square of negative 3 minus 3 times negative 3. Okay, and squaring a negative, or negative 3 times itself, that's going to be a positive 9. And then we have negative 3 times negative 3 is going to be another positive 9. And in this case, right, so that's going to come out to positive 18. Now if I go from x equals negative 3 to x is equal to 1, okay, so with x at 1, so the output I have the square of 1 minus 3 times 1. So 1 squared stays at 1. Negative 3 times 1 is negative 3. And 1 minus 3 comes out to negative 2. And just to kind of mention, okay, so like if I have x is equal to negative 3, then the corresponding y value, in this case f of negative 3, comes out to 18. So you have like a point on the graph of this function to be negative 3, 18. And another point, okay, say whenever x is equal to 1, and again the corresponding y value we have at negative 2. So another such point that exists on y is equal to x squared minus 3x is going to be at 1, negative 2. Now, in the case of variable input expressions, okay, so I have f of x plus 2, not x plus 2 squared, but x plus 2. Okay, so for extending the input from x to x plus 2, but I'm still going along the lines. Okay, so f of the input is equal to the square of the input minus 3 times the input. Now the input is going to be x plus 2. Again, just the way to look at this, I'm just going to copy this part. I guess I could have written it out. But again, you have for f of the input is equal to the square of the input minus 3 times the input. Okay, so whenever the input was x, I had x to the second minus 3 times the input of x. But now for f of x plus 2, so looking at the square of x plus 2 minus 3 times the quantity of x plus 2. Okay, now remember, for x plus 2 squared, I'm looking at x plus 2 times itself. So in this part, we'll have x squared plus 4x plus 4. And for negative 3 distributed over the quantity of x plus 2, so we have negative 3x minus 6. And gathering like terms. Okay, so I have the x squared term. For what I have in first degree in x, I have 4x and negative 3x. So that's going to be a positive x. And we have 4 minus 6. And so that will come out to negative 2. Okay, so for this variable input of x plus 2, the output is also a variable expression where we have that to end up as x squared plus x minus 2. All right, and tell you what, just kind of looking at the determination of functional values and expressions. We'll say we have given f of x is equal to 2x squared minus 3x plus 7 Let's see what we get for f of negative 3, f of 5, and say that in the case of binomial expressions. Let's see what we get for f of x plus 1. So for the next few minutes, okay, let's see what we get for f of negative 3, f of 5, and f of x plus 1 given our function f of x is equal to 2x squared minus 3x plus 7. Okay, so what, we'll go ahead and set the stage, okay, for each of these three items. Again, for f of negative 3, okay, so utilizing the function f of x is equal to 2x squared minus 3x plus 7. So here we have the input at negative 3. So we have 2 times the square of negative 3 minus 3 times negative 3, followed by the addition of 7. Okay, and we'll continue with this. And for 5 as the input, so have 2 times the square of 5 minus 3 times 5 plus 7. And again, okay, with a changeover for one variable input to another, transitioning from x to x plus 1. So you have along the same line. Okay, so you have 2 times the square of the input will be 2 times the square of x plus 1. We have minus 3 times all of x plus 1, followed by the addition of 7. Okay, so for what we have in following through, okay, so we got 2 times the square of negative 3. Now, the square of negative 3, once again, is going to be a positive 9. And here we have negative 3 times negative 3. I can go ahead and change that over to plus 9. And we have plus 7. And for what we have in following through, okay, so you have 2 times 9 is 18. And I can technically go ahead and possibly add 9 and 7 together and make it 18 plus 16, but just doing it gradually. So you have 18 plus 9 is 27. In turn, 27 plus 7 is 34. Okay. So that is saying that on the graph of this function, whenever x is negative 3, the corresponding y value is going to be 34. Okay, now looking at the y value whenever x is set to 5, and finding out what that is going to be, so y is going to be f of 5, and for the numerical value, okay, so you have 2 times the square of 5. Square of 5 is 25. So you got 2 times 25. Negative 3 times 5 is a negative 15. Okay, followed by the addition of 7. And we have 2 times 25 is 50. And we have minus 15 is 35. In turn, 35 plus 7 is 42. So 542 would be a point that would be on the graph of this particular function. Okay. Now for what we have in the case of the variable input, okay, so you have with 2 times, okay, the square of x plus 1, again for x plus 1 squared, or x plus 1 times itself, again this would be the trinomial x squared, and you have plus x, which will make 2x. And you have plus 1, negative 3 over the quantity of x plus 1, so that is going to be negative 3x minus 3. And you have followed by the addition of 7. And I tell you what, I'm just going to move down. Okay, so we got with distributing. Okay, so we got 2 over the trinomial x squared plus 2x plus 1. So that is going to be 2x squared plus 4x plus 2. You have minus 3x. And you could go ahead and combine negative 3 and 7, but we'll just do this at the end. Okay, so for what we have in the set of terms, okay, so you have 2x squared is the only second order term. For what we have in first degree, so we got 4x and negative 3x. So that will leave us with plus x. And for the constants, okay, so we got 2 minus 3 is negative 1. And then in turn, negative 1 plus 7 is a positive 6. Okay, so we have for this final outcome, okay, we had 2x squared plus x plus 6. All right. And again, just regarding what we had encountered earlier when we were looking at sets of ordered pairs. Okay, we had dealt with, again, domain and range, okay, where domain is the set of x values and the range, okay, we had to be the set of y values. And now in the case of what we have for functional notation, now we're going to for a bit, okay, put the term range at bay and focus at the moment primarily upon domain. And but again, range will eventually re-enter the scene. Okay, but for right now, for the domain of a function, okay, now whenever the function is given as a set of ordered pairs, domain is just the set of x values. Okay, but now in the functional notation, okay, we'll be sort of looking at combining, okay, what we have in x along with just what we have worked with, going back to restricted values, like in terms of avoiding, something like a zero denominator in a fraction, and just kind of a fine-tuning approach to defining the domain of a function. Okay, so for the domain of a function, y is equal to f of x. Okay, and for the domain of a function, y is equal to f of x. Okay, we're going to have the set of all x values such that f of x is defined as a real value, or defining the set of all real numbers. Again, just for the interval notation, you have between negative and positive infinity. All right. And just for what we have in the case of the domain of a function now, some of the functions might have the domain to be all real numbers, and you might have those that might have limitations where you're going to have some restricted values. Now let's say that if I'm looking at determining the domain using interval notation. Let's see what we have first of all. Kind of like whenever we started out with y is equal to 3x plus 4 in the vertical line test graphing. So you have like f of x is equal to 3x plus 4. Okay, so you have a straight line like what we had as the first graph whenever we were using an example or case of the vertical line test. Okay, if you notice, okay, we have with f of x is equal to 3x plus 4. There's not like a fraction or an even root radical or any of that. So for what we have for f of x is equal to 3x plus 4, okay, there will be no restrictions. And what I mean by restrictions would be like in terms of what x cannot be. So in other words, what I'm saying is that x can be 0, it could be a positive, it could be a negative, and there will still be a corresponding y value that'll be within the real number system. Okay, so if there are no restrictions, okay, you're going to have for the domain again, that's going to be the set of all real numbers Okay, so you have parentheses around negative and positive infinity. Okay, now let's say if I change the dynamic, okay, just a little bit, and I'll have that f of x will be given in direct terms. So we have, let's say, x squared minus 4x minus 17. Again, I still don't have a fraction or any particular radical. Okay, so for x squared as well as negative 4x, I can plug in any real value for x and not upset the apple cart in terms of having an output that is defined. Okay, so we have this bit of history to repeat, so there'll be no restrictions once again, and we're going to have the domain to still be the set of all real numbers. So these first two functions, okay, no restrictions, and we have the domain to be all real numbers. Okay, now let's say that if I have f of x, and we have is equal to 3x plus 4, and say we have all over x minus 5. Okay, so we got 3x plus 4 over x minus 5. Okay, now this time around, okay, I got a ratio, and for fractions, the bottom part of a fraction cannot be 0 in value. Okay, so this time around, there is a limitation in terms of what x is allowed to be. And that limitation comes from the fact that the denominator cannot be 0. So we have the x minus 5 cannot be 0. And if that is the case, then we have the x cannot be equal to 5. And just putting in terms of interval notation. Again, just providing a bit of a visual. Okay, so again, so you had the excluded value is going to be at 5. Anything that is not 5 in the real numbers is going to be in the domain. So you have everything greater than, as well as everything less than, is going to be in the domain. And the way to look at this, okay, is that for the domain. Instead of having a line that runs continuously at both ends, I have broken up into two portions, and for the lower left section, for the line segment array rather, going continuously to the left, I have in the direction of negative infinity, and on the side of where we have greater than 5, we have continuity out to infinity. Okay, so for representing both of these portions in interval notation, okay, so we have for the first part of the domain, we're looking at between negative infinity and, but not including 5. So you have a parenthesis, and then you have 5 is going to be bypassed. Okay, and so we have union with the upper set of values. It'll be those values greater than 5, and the interval notation, in this case, will be parentheses around 5 and infinity. So in interval notation, the domain of this rational function is going to be a union of intervals. All right, and let's say that if we have a function f of x and say we have 2x squared plus 3 all over x squared minus 16. All right, so you have another rational function, and again, the restriction for a fraction is going to be that the denominator cannot be 0. So this time around we have the x squared minus 16 cannot be 0. And with x squared minus 16, okay, we have a difference of squares whereupon we can factor. Okay. All right. So this is going to have a feel of the zero product property, but instead of setting to 0, we have it in terms of specifying what is going to be restricted. Okay, so where we would have x plus 4 and x minus 4 equal to 0, we're hunting down the restricted values. So we're going to have the setups whereupon we have x plus and x minus 4 cannot be equal to 0. So if x plus 4 cannot be 0, we have the x cannot be equal to negative 4. And for x minus 4, if that cannot be 0, then we have the x cannot be equal to positive 4. Okay, so in looking at what we have now, okay, so you have a couple of restricted values with negative and positive 4. Everything else from the real number system is going to be included. Okay, so for not equal to negative 4, I can signify by an open circle. And likewise, since x cannot be 4, I'm going to place another open circle. And just for the formation, then we have separate sections, okay, for the graph of the domain. Okay, and so for what we have in the case of the domain, okay, if you notice you have 3 sections that are now formed, and there's going to be a pattern, kind of inductive, where it's like, if you notice we had like one exclusion with 5, from which we had 2 separate sections. And guess what? We now have 2 restricted values, and now we have 3 separate sections. And so what happens here is that with the more restricted or excluded values there are, the greater the number of sections there will likely be. Okay, and so for what we have in the case of the domain of this rational function, okay, so we have first case, right? So we have with the extreme left. Okay, so you have between negative infinity and negative 4. Once again, negative 4 is not included. So that's going to be in the parentheses. And then we have for the middle strip, okay, so you're looking at those values between but not including negative and positive 4. And for the interval notation, so we have parentheses used to enclose. And then finally we have at the upper end for values of x greater than 4. Again, you have a parenthesis around 4. And again, infinities run continuously, so we have parentheses throughout. Okay, so that'll be the interval notation for the domain of what we have in example 4. All right. And for what we have in the case of changing it up, say going from a rational to a radical function. And say we have that f of x is equal to the square root of x minus 7. Okay. Now with the nature of the radical being an even root, and since we're looking at real numbers, not complex numbers this time around, so you have for an even root radical. Okay, so we have the x minus 7 cannot be negative. All right. Now with the square root of x minus 7 given in direct fashion, I can have the square root of 0 and I can have the square root of a positive. And so in this particular case, all right, so it just can't be negative, but it can be 0 or positive. So I can just kind of set things up along the lines of an inequality. So for x minus 7, it can be equal to 0. It can also be greater than 0. So we have that x minus 7 is greater than or equal to 0. And so looking at isolating x. Okay, so you have that x is greater than or equal to 7. Okay, and in terms of, once again, how that would look in terms of interval notation. Okay, so the value of interest we have at 7, and with an equal sign, okay, so we have a solid point at 7, and the rest of the values x will be greater than. And so we have in graphing, so there will be continuity out to the right, heading in the direction of positive infinity. Okay, so for the domain, of this rational function, okay, so we're going from 7 to infinity. And for the enclosures now, okay, now 7 is included, so it is part of the makeup here. So 7 is now going to be bracketed, but again, infinities are boundless, and so infinity stays inside the parenthesis. Okay, so that would be the interval notation for the domain. Now, and just kind of serving as a reminder concerning inequalities. And say if I have subtraction of the variable, if I have, like, say, the square root of 8 minus 2x, again, because we have an even root radical with a square root, just like with x minus 7. Okay, we have that 8 minus 2x cannot be negative. And just like x minus 7, 8 minus 2x can be 0 or positive. Okay, so just setting up as an inequality, so we have the 8 minus 2x is greater than or equal to 0. And looking at solving for x. Okay, so getting the negative 2x by itself. Okay, so if I take away 8 from both sides, so I'm going to have negative 2x is greater than or equal to negative 8. And then getting in terms of x, so I'm back in the terrain of multiplying or dividing by a negative. So again, whenever you multiply or divide by a negative, the direction of the inequality will change. Okay. And so for what we have now, we end up with x is less than or equal to positive 4. Okay. Okay. And so just looking at it from a visual standpoint. Okay, so we have 4 as a limit of interest, and thanks to the equal sign, 4 is included. So you have a solid point. Everything else will be less than 4. And so you have the ray running continuously to the left, crossing over into the negative zone and heading in the direction of minus infinity. And so we have for the domain, okay, so we have going from negative infinity, approaching and including 4, and here 4 is going to be in the bracket. All right, so we kind of started out with functions like linear quadratic functions, where we have the domain to be all real numbers, and again you have rational functions where we have zero value denominators disallowed. Okay, so we had like limitations in terms of the domain. Okay, like in the case of examples 3 and 4, we no longer have the set of all real numbers. And again, we have with radical functions with even roots, again, whatever is inside the radical cannot be a negative value. And so we have these one direction inequalities. Okay. And now let's say if you have a bit of a combination of rational and radical. And I'm just going to cap this off. Okay, and say if we have that f of x is equal to, let's say we have x minus 13 all over the square root of x plus 10. Okay, now for what we have in this particular case, right? So you have now we have x minus 13 all over the square root of x plus 10. Now in terms of restrictions, okay, nothing is going to come from the numerator, x minus 13. However, with x plus 10, okay, we have a bit of a twofold situation. Okay, first of all, okay, we have with x plus 10, again, we have with the square root. So we have that x plus 10 can't be negative. And if I had the square root of x plus 10 given in direct fashion as opposed to where it is situated in the denominator, I could say that x plus 10 could be 0 or positive. But guess what? Because x plus 10 is in the denominator of the fraction, we have that x plus 10 cannot be 0. So filtering out, leaving out the negative aspect as well as the 0 aspect. So that means that x plus 10 must be positive. Okay. And in terms of the inequality setup case, you have for x plus 10, if it is to be positive, well, x plus 10 is going to be greater than 0. And so looking at isolating x. Okay, so just taking 10 away from both sides. Okay, so we'll have for the domain, the defining inequality is going to be values x that will be greater than negative 10. Okay, so with negative 10, as the numerical value of interest. Okay, so without the equal sign, negative 10 is not included. So you have an open circle, and again, our values of x will be greater than. So we'll have the activity heading out in the direction going toward infinity. Okay, so in the case of the domain, so we have going past negative 10 and approaching infinity, right? And again, negative 10 is not included, so that's going to be in the parenthesis. And again, since infinities are boundless, okay, have infinity again in the parenthesis. So for the domain, in the interval notation, we have parentheses surrounding -10 and infinity.